Hey guys, welcome to the second part of lesson 2.1. So a couple things we're going to go through on this. As always, I'll try to keep it moving for you, so feel free to pause and um, at any point along the way in case you need to take a further look at something. But we're going to be focusing on what they call the tangent line problem in this section. So tangent line, just the line that would connect to any other function at a given point. So for example, if you had, say, a curve that looked like this, and I have a point right here, and I drew the tangent line that goes through that point, that's what we're focusing on right now. So this would represent the tangent line that hits the other function at this point. As a couple quick things of notation issues, here are just several ways that you can be asked to find a derivative. So when you find a derivative, it can come to you in any of these forms. The first three are the most popular. So f prime of x is a real common one. dy over dx is a real common one. And y prime. So those are the three most common. Here's just a few others that you can run into. I just wanted you to know that anytime you see any of those, they all mean the same thing, right? They're all asking you to find the derivative of a certain function. So if this was the original function, f of x, right, they may say something like find f prime of x, which means find the derivative of that function. As you look kind of down at this next line, the process of finding a derivative is called differentiation. So let's throw that one into our first blank here. So differentiation is the process of finding a derivative. So we would say a function is differentiable So a function is differentiable if its derivative exists and it's differentiable on an open interval. And I'll give you an example of that here in just a second. Let's just fill in the blank. So, and it's differentiable, I'm going to abbreviate. So differentiable on an open interval. So there are some functions that, or at least certain points on functions where you cannot differentiate it. In order to differentiate at a certain point, because remember, that's simply finding literally the slope of that function at a certain point, right? That's what a derivative represents. It's literally the slope at a certain point. But in order to do that, it's got to be some kind of a smooth curve or a line. It can't be something rigid. So for example, if you look at the absolute value graph that does something like this, right, at that point right there, because this is not a smooth curve, this function is not differentiable at that point. It is differentiable in other intervals within that function, so you could be asked to find the derivative at some other points, but we'd have to recognize that at this point right here at the vertex, it would not be differentiable. The same would go for something that we call a cusp. So if it does something like this, all right, so if I had a function that did something like this, again, if this is what we would call a cusp, and not something that we could find the derivative of. You could not draw a tangent line to this point right here the same way that I did on the smooth curve that you see up above. All right, if it's differentiable at every point in the interval. So again, if they said we're looking at from here to here, it would not be differentiable at every point within that interval. But if we only limited it to, say, from this point to this point, well, within that interval, it would be differentiable. So it just depends on the interval that we're taking a look at. So the second thing we're talking about is continuity. So differentiation implies continuity. So if a function is differentiable at x equals c, so when x equals some number, then it means that the function is continuous at x equals c. So let's say f is continuous at x equals c. So that means it would have to be continuous at that point. So for example, And here's something we've seen before. So if we had something like this, right? So even though this point does exist, it is not continuous at that point, so we could not differentiate at that point. Jumping on down to this one, so right here we have what we call our difference quotient. And we've talked obviously quite a bit about limits in the previous chapter, but consider the limit as delta x approaches 0 of any function, right, within our difference quotient. If you are approaching positive infinity or negative infinity, then we know that we are approaching a vertical line at that point, right? So remember that if we have, so let me just throw in a vertical line right here. So if I had a vertical line on that graph, as I approach that line from the left or the right within any function, right, you can't cross over that vertical line, so my graph would have to either head upward toward positive infinity, or it would have to head downward toward negative infinity, right? And so we know that if we're ever approaching infinity, then we know we're approaching a vertical line. All right, jumping on down to this one, I'll show you a little calculator stuff for this next part. So if you have a TI-84 handy, I'm going to show you a couple things on there. So let's just say we had the function x squared, right? You guys are obviously familiar with x squared. It would just be a parabola. So this would be at 0, 0. So if we said, what is the slope of the tangent line where x equals 1? So if I jump over here to where x equals 1, and I drew a tangent line, and I want the slope of that tangent line, we can get that with our calculator. So this would be a very easy one to do by hand, because all you would have to do is find the derivative and then plug in 1 for x into the derivative. But this would obviously be really helpful with some more complicated problems. So let me show you real quick, and I have all the directions in here for you, so you can always have those to look back on. But essentially, we're going to go to our math button. So right here, I'm going to hit the math button, pulls up that menu, and then option 8, where it says n deriv. We're going to choose that one, and then we're just going to plug in the items. And you're seeing over here what it is that we're plugging in. So we're doing d over dx. So I'm going to throw an x into that. And then within those parentheses, we're going to put the function that we're deriving. So in this case, our function was x squared. And then right here, we're simply telling the calculator at what point do we want the slope. And in this case, we wanted it where x equals 1 was our goal. So we're just going to throw in a 1 for that and hit enter. And so that tells me that the slope of this tangent line where x equals 1 has a slope of 2. Would be the slope of that line. And so that's a great tool. There are others in here. You can do it with within the graphing tool. We can look more at those later, but that's one I wanted to show you guys now. Let me go on down to this one. So alternative form of the definition of a derivative. So this is one that we would use when we're looking for the slope or the derivative at a specific point, and we just want the numerical slope. Pretty much just like the one that we just found where we said our slope was 2. So when we want that rather than an expression in terms of x. So the expression in terms of x would get us multiple slopes for whatever x represented, right? But if we just wanted one specific slope at a certain point, we're using basically the limit as we approach our value within our difference quotient. So if we said the limit as x approaches some number, so as x approaches c, we're essentially just saying we're just looking at the rate of change or the slope. So basically y minus y over x minus x. Same thing as our slope formula. All right, let me flip the page for you. So jump over to this one. So for this example, now instead of just finding the slope of the tangent line, we actually want the equation of that line. So think back to like your y equals mx plus b, right? That's what we're trying to find with the equation of this tangent line. Typically, as you've done in the past, we start with our point slope formula, which looks something like this. And of course they call it point slope because you need a point and a slope. So for this example that we're going through right here, we are given the point. We just need a slope, which naturally means we need a derivative. So we're going to use our difference quotient process where we always let the first x value be x plus delta x, and then the second one is simply x. So we're looking at, and this is where the denominator comes from, this is simply x plus delta x minus x, right? And that's where we're getting the change in x that we're seeing right here. And the goal is to find where that delta x, where the change of x approaches 0, simply because we want this at a specific point. This is not within a range of points, right? And so we're looking for just the specific point. So on top of this, we're doing f of x plus delta x. So in other words, I am plugging x plus delta x in for this in order to get my first y value. So that one's now going to be x plus delta x to the third. So I just replaced x with x plus delta x in order to get my first y value. And then the second one, we're always using f of x, which is just the function itself. So it looks something like this. So again, remember, this just goes back to simply y minus y over x minus x, right? So it's really just a slope setup. So we just got to do some simplifying here. So we're going to start by expanding that guy right there. Let me throw in the formula that I'm using as a quick reminder. So the formula you learned in the past for expanding a binomial to the third looks something like this. This is definitely one you should memorize because we do use it quite a bit. So if I apply that to just this first part of the expression, we're going to be looking at x to the third plus 3x squared delta x plus 3x delta x squared plus delta x to the third and then I'm just going to bring over the minus x to the third. So there's what it looks like after we expand. Jump down to this line right here. So we're just going to start combining like terms. So like for example, you see how the x to the third and the negative x to the third cancel. So if we do a little simplifying up there, we're going to end up with 3x to the second plus 3x delta x plus delta x squared. And again, just a reminder on where all that's coming from. So those x's to the thirds canceled. Everything else I was left with all had a delta x in it. And so because of him, I just divided everything by delta x to get this next line that you see right here. So that's what we got right there. And then remember, if delta x is approaching 0, now I can do direct substitution. So this becomes 0, this becomes 0. I'm simply left with 3x squared. So 3x squared now represents our derivative, right? And we used our difference quotient to get it. So we can now use that derivative to find the slope at any point within that function. And it just so happens the one that we need is where x is equal to 2. So if I take that 2 and plug it into here, so our derivative is, let me just fill this in. So our derivative is 3x squared. So f prime of 2, because of him, would look like this. And if we just do a little cleanup on that, we get a slope of 12. So we now know the point. We now know the slope at that point is 12. And so now we can go on to write the equation of a line. We're going to use our point slope formula that we have right there. So we're going to say y minus the y coordinate equals our slope times x minus the x coordinate. So that's what it would look like in point slope form. If you distribute the 12 and then add the 8 over, you would get y equals 12x minus 16, which is typically the way that we want to write it. We want to put it into y equals mx plus b form. All right, let me jump down to this next part. And then real quick, what we had talked about on the previous page of using one of our calculator functions. And so if we wanted to check our answer, so if I go down to that 8th option of n deriv, d over dx, our function was x to the third. And we wanted the derivative where x equals 2, right? And so we get this right here. So why does the calculator say 0.00001 rather than just 12. So remember, this whole idea is this is technically a limit, right? When we talk about an instant rate of change or a derivative, we're really talking about the slope that we are approaching, right? It's never actually landing on that value. It's simply the number that you are approaching. And so we are approaching a slope of 12, so we would just say our slope is 12, right? And so it's up to you guys to be smart enough to recognize that, hey, based on this, my slope is 12. All right, let me jump down to this one. So just as a side note, something I mentioned on the previous page, that a function is not differentiable at a cusp, which is like a sharp point, or at a vertical tangent line, right? The slope is undefined at a vertical line. So it has an undefined slope, so it would not exist in those types of cases. So let's take a look at sketching the graph of the derivative of the graph that you guys see here. All right, so let's take a look at sketching the graph of a derivative. So here is just kind of a random drawing of a function, and we're going to see if we can come up with a drawing of the derivative of that function. So I'll kind of do this on a separate grid just so we can keep things separate. But one thing we want to understand about this is when you draw the derivative, the y-coordinate technically represents the slopes of this graph right here, right? So it's like we're using the same x's that they use, but the y-coordinates that we come up with are going to be the slopes at different points within that drawing. Let me just set this up here, and then we'll draw it in. So let's identify just kind of the common things going on within this graph, though. So here's well, it looks like sort of a quarter circle that we're seeing right here. So let's just talk about that guy first. So at -2, right? So if this was, say, a quarter circle, right, and it comes down and at -2, it's now completely vertical. Well, we know that at this point, then it would be undefined, because if I have a vertical tangent line right here, which it looks like we do, right, then technically at that point specifically, we undefined. So when I start to draw over here, I know that at -2, I should have an undefined or an open circle at that point. However, for the rest of the circle, this is all positive, right? So if you were to draw the tangent line at any point within this curve, your tangent line would be going up and to the right, which means it's all positive. So every point on that curve has a positive slope. Now, it starts out with a really big positive, right? This would have a very steep positive tangent line right there. So it starts out with a very big positive, but as you go further to the right, those tangent lines start to get flatter, and so it's approaching 0. So it starts out with a really big positive, and as we get closer and closer to this point, we're closing in on 0, right? Because if this does flatten out, which it looks like it does, so the tangent line, once we get to that point, is then essentially 0, right? So here's kind of what we're seeing. Just from -2 to -1, we're seeing it was undefined. It was a very big positive. And as we get closer to -1, we approach a slope of 0. So we're getting really close to a slope of 0. We'll talk about this, why this is an open circle. Let me just draw it first. So at -1, so I'm going to have an open circle there at my slope of 0. And I'll show you why in just a minute. But at -2, it was undefined. And then again, we said it was a really big positive and gets closer and closer to 0 as we approach -1. So it started out with some really big positive number. We're going to have to put an open circle there because it would be undefined at -2, since there's a vertical tangent line right there. And then we had very, very big positive, and then it gets closer and closer to 0 as we get to -1. So it looks something like this. So why would it be an open circle right there? Well, as you look at what happens as we approach -1 from the left, and what happens as we approach -1 for the right, do they have the same slope? Well, this one is approaching a slope of 0 from the left, but as I approach it from the right, well, what's the slope that we're seeing going on right here? This, from the interval of -1 to +1, this is just a line. right? And that line is going down 1 over 1, down 1 over 1. So every point on this line has a slope at -1 because it was going down 1 over 1. So this has a slope of -1. This side has a slope of 0. It's approaching 0, right? And so obviously those slopes don't agree with each other, and which is why it would have to be undefined at that point. So it's approaching 0 from the left, and then as we land on 0, it's undefined. But what about to the right of that? So from the interval of -1 to +1, the slope, because it's a line for this portion, the slope everywhere at this point on this, every point on this line would have a slope of -1, which means from -1 to +1, my y value or my slope is always -1. So let's put -1 right here. So from -1 to +1, my slope is always at -1. So we get this horizontal line at -1 because every slope from here to here is -1. And remember, we're treating the y-axis as our values of slope, since this represents the derivative. Then as we go from 1 to 2, so for the final interval from 1 to 2, what are the slopes? Well, from 1 to 2, this is now going up 1 over 1, and it's constant, it's a line, so the slope's not going to change. So from 1 to 2, my slope is always 1, right? Because we went up 1 over 1. So from 1 to 2, I always have a y value or a slope of 1. So from 1 to 2, so if 1 is right here, so from 1 to 2, I have a slope of 1. And again, it's constant, so I'm going to have a horizontal line for that part. Why are these undefined? Neither one of those are filled in for the same reason that we talked about with this one, right? We already said up top that if you have a sharp point, it's undefined. And again, it's because it's not a smooth curve. We talked about the slope on either side of it. These guys have different slopes. So as you approach one from the left and from the right, you have different slopes. And so because the slopes don't agree on either side of it, it has to be undefined at that point. Couldn't take a derivative, right? And the same would be true here with the sharp point that we have it too. Okay, so let's move on to next page. Okay, so for this final page here, we are looking at piecewise functions, and we're trying to determine the derivative of a piecewise function at a certain point. So as we look at something like this, a piecewise function, as you should have seen in the past, is where you have two different functions on values. So for this first example, we're going to be looking at to the left of 1, we have this function, but to the right of 1, we have this function. So we have two different functions on either side of where x equals 1. All right, so there's two things that we're going to have to consider here to see if we can come up with a derivative on this, and that is it differentiable, and is it continuous at that point? So in other words, for this first example, where x equals 1, these graphs have to connect, so it has to be continuous, and differentiability means it's got to be approaching the same slope from both sides. So both of those things need to be true in order for us to examine a derivative on this. So let's just talk about the derivative first. So if we were to take the derivative of x squared, and we looked at finding the derivative of functions like this earlier on. So if we wanted to find the derivative of x squared, we're simply going to get the function 2x. And if I wanted to find the derivative of this, we know it's going to be -1. Why do we know it's going to be -1? Well, remember, this is just a line, right? This is in the form of y equals mx plus b. So m, the slope, is -1 everywhere on this line, right? Because a line has a constant slope. And so it's just going to be a constant of -1 everywhere to the right of this guy. Okay, so those are the two derivatives on either side of where x equals 1 for this piecewise function. As you look at this part of it, which we'll be talking about here in just a second, so whenever you see f prime of x and you see the little negative right there, this one has the positive. So similar to limits, this just means the left side, and this means the right side when you see that minus or plus. Okay, so so we will be looking at this here in just a minute to determine if this graph is differentiable. But we look at the original function just to determine whether or not it's continuous. And so let's just start with that. So if we look at the original function, is it continuous at this point? So as you approach 1 from the left, so now it's referring to this function right here. So this represents x's that are less than 1. So as we approach 1 from the left, what would we get? Well, if I plug in a 1 to this function, 1 squared is, we'll just write it out so you have it for your notes. So we know 1 squared is obviously 1. As we approach right, so this one, according to this domain, tells me that this is the function as you approach 1 from the right. So as I plug a 1 into this x, I get negative 1 plus 2, which is simply 1. Right? So we know this graph is continuous at x equals 1 because of the y values that we got right here. Right? So as we plugged into that function, because you got the same value right here, we know it's continuous at 1. Now, if these numbers did not match, that would mean it's not continuous, and therefore we could not take a derivative. Let's look at the second part. So now if we consider differentiability, we need to now take a look at the derivatives and see if the slopes are the same on both sides. So as we look back up now at these two functions, so as we approach 1 from the left, so here's the one for x is less than 1. So as we approach 1 from the left, so if I put in a 1 right there, so 2 times 1 is 2. So that tells me that the left side of this is approaching a slope of 2. What about the right side? Well, on the right side of this, for x is greater than 1, so the right side, the slope is always negative 1, no matter what. So this one to the right side of 1 always has a slope of negative 1. Obviously, those are not the same, which means just like in the graph that I showed you on the previous page, it was undefined at certain points because the slopes were not the same on either side of that point. Right? So if this one is approaching a slope of 2 and this one's approaching a slope of negative 1, as you land on this value, it has to be undefined, and it's not differentiable at that point. So we're going to simply say that these guys were not equal. So therefore, it must not have been a smooth curve. So let's just say not a smooth curve. So therefore, we cannot differentiate. Okay, so if they had, and you saw this on the last page, here, I'll just show it to you real quick. So you guys saw within this example, right, we had these open circles because you couldn't get a derivative. It was undefined. It wasn't differentiable at points like this because we said this slope was approaching of 0 to the left of negative 1, but to the right of negative 1, my slope was always negative 1. So because they had different slopes on either side, it had to be not differentiable at that point right there. All right, so let's jump down to another one. So let's look at a similar idea here. So again, as we've already talked about, we know that the derivative of x squared is 2x. And because this is a line and the slope is 2, this one, the derivative would always be 2. So the slope is always 2 according to that domain. Okay, so this is the slopes that we're getting to the left of 1, and the other one is where we're getting to the right of 1. So we're going to start this one just by looking at the slopes. So first things first, is this thing differentiable? So do I get the same slope on both sides of 1? So we're going to plug into this. So again, because of this is a value of 1, right, is why we're plugging in 1s. So for x's, as we approach 1 from the left, which means I'm looking at x's that are less than 1, so I'm going to plug into this function. So if I plug in a 1 to this, I get a slope of 2. Well, what about as we approach 1 from the right? Well, for x is greater than 1, so as we approach from the right, the slope is always 2. So according to this, because they are equal, the left and the right sides, we'll say the left and the right sides approach x equals 1. At the same slope. So far so good. So left and the right sides are both approaching the same slope, so that's good. Now we need to check continuity. Is the graph continuous at x equals 1? And this is where you go back to the original function. Does this graph meet this graph at this point? Right? It's got to be continuous. So even though they have the same slope on either side, you could still be looking at a case like this, right, where those graphs have the same slope, right? Those are parallel lines, they have the same slope, but they're not continuous because they're not connected, so therefore they're not differentiable. So that's what we're checking, right? Is it continuous, or is there some kind of discontinuity in the graph at that point? So let's look as x approaches 1 from the left. So going back to these guys, these are x is less than 1, so this is one we got to look at for the values that are approaching 1 from the left. So if we plug in a 1 for this x, 1 squared is 1. As we approach 1 from the right, so now I'm looking at this domain, so I want to plug in for this, 2 times 1 plus 1 would be 3. So these guys are not equal, which means this graph is not continuous at x equals 1. So f is not continuous at x equals 1, so this is not differentiable. Oops. There we go. So again, both of these have to be the same as each other. Those have to be the same as each other in order for this to be possible. So we're going to look at one last example. All right, so going to these guys, and I'll go a little quicker through this one now that you've seen a couple. We know the derivative of x squared is 2x. The slope everywhere on this line is 2. So let's take a look. So we're going to check for continuity first. So when you use the original function, you're checking for continuity. So as x approaches 1 from the left, so according to that domain, I'm going to plug into this. And by the way, this isn't always 1. Right, these examples all have a 1, but whatever values you see here, that's what this number would be, and that's what we would be plugging in for x. So as we approach 1 from the left, so 1 squared we know is 1. As we approach 1 from the right, so that's this domain, so 2 times 1 minus 1 is also 1. So far we got a winner. This is continuous because those are equal. We would say the graph is continuous at x equals 1. So now we're going to check the slopes on either side to see if the slopes match up. So as we now look at the derivatives of this, if I plug in a 1 for values to the left of 1, so 2 times 1 is 2. And the other side of 1 always has a slope of 2. So these guys are also a winner because they have the same slope. So we can safely say that this is differentiable where x equals 1.